or a volcano was looking for somewhere to live, and he was trying to find a place that was quiet and there were no cockerels.
You're listening to the Cosmic Cast.
Hello and welcome to the Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. This week we have John Pernay-Fisher.
Hello.
Tom Harvey, somewhere up there.
Hello.
Ricky Bahir.
Hello.
And our guest this week, it's volcanologist Brendan McCormick Kilbride.
Hi.
How are you doing, Brendan?
Yeah, very good. Very happy to be here. Thank you.
So I believe you're a presidential fellow here at Manchester.
Yes.
And you've been in Manchester since about last January, is it?
So, well, it's coming up a year. In fact, next week it's going to be a year since I began in Manchester.
Oh, great.
So I have fond memories that although I was missing the EGU meeting in Vienna, I was starting a new job. So, and the sun was shining.
Oh.
The building in brilliant sunlight, and it was a good way to start. But yeah, I've been there just about a year now, and the presidential fellowship is a, I guess, fairly recent scheme that the university launched, and it's across all of the different faculties, and essentially it's a tenure track style position. So we are appointed for 4 years, and the idea is at the end of that 4 years you pass probation and sort of graduate as a lecturer. And the idea is, or the principal idea of the 4 years is that you're given like a big period of autonomous time to kind of establish yourself as an independent researcher. And along the way, there's kind of a structured phasing in of teaching responsibilities and sort of service responsibilities within the community of the department and the university. And I guess the hope is that for all of us, we as a cohort kind of sort of graduate together and become like a new generation of university staff. So it's a really exciting program because there's lots of cool people doing all kinds of different work. So it's all fun when we get together and meet each other.
That sounds great. And I believe your research area is looking at volcanic gases.
Yeah, that's right. So I'm a volcanologist, and I particularly study volcanic gases. So the Earth has hundreds of volcanoes, and even if they're not erupting, very many of those are active in other ways. And one of the important ways that volcanoes kind of persist in their activity between eruptions is they emit gas. So magmas contain quite abundant volatiles, things like water, carbon dioxide, sulfur dioxide, down to sort of more trace species like the halogens or noble gases. And these volatiles are released from a magma by a number of different processes beneath volcanoes, and if they rise to the surface, they can escape through vents. And we can measure the chemistry and the flux of those gases out of volcanoes to get an insight into some of these subvolcanic processes.
So I believe you've used a lot of different techniques for looking at different gases. So obviously you can use like satellites. So we've had a lot of guests talking about volcanic gases like Kat Heyer, but then also people looking at more ground-based techniques. What sort of things do you use to look at gases?
So I've kind of tried a number of different things over the years, and the motivation at the moment really is to find ways to integrate different techniques in complementary ways. So my first experience of volcanic research during my master's project was about going into the field and recovering samples from a volcanic crater, like collecting gas samples or collecting volcanic material, so rocks or soil samples and like the substrate, and analyzing those for volatiles in the lab. And the majority of my PhD work was using satellite observations, so remote sensing. And since then, as a postdoc, I've been trying to bridge the gap between those two. So I guess the shorthand way I describe it is a mix of satellite-based, field-based, and lab-based methods.
That's interesting. So really sort of putting that link then between what's in the ground and what we see in the atmosphere.
Yeah, exactly. And each of these has its own sort of strengths and weaknesses. So satellite observations are very effective at giving you this sort of synoptic picture of the world's volcanoes. But we are restricted to sulfur dioxide emissions, broadly speaking. among the major magmatic volatiles. And until very recently, well, so let's say there are limitations to the satellite observations in terms of the spatial footprint of the, like, the sort of pixel resolution of the satellite's view, and also how often you repeat a flight over a volcano. So these are kind of hardwired limitations into any generation of satellite instrument. So if you want to study different chemical species, or you want to study things on a finer temporal or spatial scale, you really need to go into the field on the ground and either climb up to the crater yourself, or use a drone or some other means of getting there.
So what sort of gases have you been analysing? Are you analysing quite a broad range, or are there some specific trace gases that you're interested in?
So to date, most of my PhD work was looking at sulfur dioxide, and the work since then has been focused on major gas chemistry, so measuring sulfur dioxide to carbon dioxide to water ratios in the field. Where I would like to go next, one of the motivations to come to Manchester was to study trace gases, and particularly noble gases, but I'm also interested in methane and nitrogen. So these are gases that make up they're much less abundant in the volcanic plume than carbon dioxide, water, and sulfur dioxide, but they can give us really useful indicators as to where those volatiles are coming from. So when a volcano is emitting gas, it all comes from the magma. Those volatiles are dissolved in the magma initially, but you can think of the gas coming from a volcano as like a cocktail. There's a number of different potential ingredients to it, and one of these is the mantle. So the mantle is the origin of the magma that drives volcanism. But particularly in a subduction zone, you can have additional contributions to the volatile budget of that magma. So it might be that there is material on the subducting plate that enters the magma generation region during subduction, or it might be that rising magmas interact with country rocks in the crust. So carbonate is a good example. You kind of bake it with a hot rising magma and drive off a lot of excess CO2. So you can kind of pollute the native volatile content of a magma by these additional interactions. And the sort of, I guess, abundance and isotopic makeup of more trace gases in that cocktail can give us some useful insight into volatile source and volatile origins.
Okay, interesting. So rather than looking at eruptive style, then you're looking at the origin of magmas, rather, basically.
Yeah, so I guess that's where my interests are moving at the moment, though it's true to say that a lot of measuring volcanic gases is very relevant to volcano monitoring, because different gas species exsolve from the magma at different pressures. So the measurements that we would tend to make in the field of the changing ratios and changing fluxes of different gases coming out of volcanoes, I think are always going to be relevant in a monitoring capacity, because they give you some insight into the state of unrest.
Yeah, that's really cool. So what kind of volcanoes have you been to collect gases from then? Where have you been?
So most recently I've been working in Papua New Guinea, in the Southwest Pacific. Though prior to that, I've done field work in Italy. I mean, I'm supposed to be in Italy in about a month's time, but that isn't going to happen. But so I have some projects in Italy, and then with the remote sensing, I've done work in Ecuador and the Marianas as well. So there have been quite a lot of, I guess my work's been quite broadly dispersed, but that's more on the remote sensing side. So in terms of the direct sampling, or the in situ measurements, that's been in Papua New Guinea. And the reason that I'm interested in PNG is that there are several very strongly active or strongly degassing volcanoes there. So we know from satellite observations that 4 or 5 of these volcanoes are among the world's leading sulfur dioxide emitters.
Oh, really? Interesting.
But we really don't know very much about the volcanoes. There's very restricted ground-based measurements available. The petrology is relatively restricted. There's a lot of kind of arc scale whole rock studies where people have sampled like a big suite of lavas, and they maybe make these sort of like synoptic studies, but there's a lot less kind of detailed, focused work on many of these volcanoes. They're less well understood.
Just trying to remember some of the regional geology there. Is that related to some of the arc volcanism you see in places like Indonesia and Java and other places, or?
Yeah, so this is I guess a little further east. So it's a different subduction zone, but it's the Western Pacific. So part of what we call it, the Ring of Fire. So you have a lot of active subduction there. Broadly, the tectonic setting, I think, is complex, and I'm by no means an expert in that. But broadly, what you have is the Australian continent and the Pacific are converging, and initially, I believe it was the Pacific subducting beneath the sort of Indo-Australian continent, and then a few million years ago, the Pacific, the portion of the Pacific plate that was undergoing subduction, was kind of consumed, and the Ontong Java large igneous province kind of docked with the subduction zone, and that's very, very difficult to subduct. So I think what happened is that then the subduction flipped and started going the other way. So basically there's this kind of, I guess, 1,000-kilometer wide crumple zone between these two big chunks of plate, and PNG is in there, and there's lots of little microplates getting kind of shunted around and scraped past and up and down and over each other, and there's a ton of volcanism of different ages in there.
Right,
and
that's really cool.
It's really, it's an interesting place. The convergence rates are really high. Some of the slabs are dipping really, really steeply, and then there's some just kind of crazy stuff of like foundered slabs, or slabs that kind of like look like they're in a sort of, I don't know, like a sad smiley face, just kind of hanging there underneath where they were subducting. And so that is appealing as well. And there's this kind of cool, if you're trying to think about the sources of volatiles in a kind of like geodynamic context, like so how maybe the material that is being subducted and how that varies spatially and temporally, and how that influences gas chemistry. This is potentially like quite a good place to do it, because there is that diversity of tectonics. It may also make it a intractable problem because there are too many variables. And yeah, as like things like the tectonic history of the area is I guess it's not as well constrained as some other arcs, let's say.
I suppose is that in part due to the difficulty in doing field work out there? I suppose it's quite remotely populated and probably quite densely full of jungle, I guess.
Yeah, so a lot of the terrain is very difficult to get around. So there's a lot of islands, and these are then either, as you say, like highly mountainous or volcanic or densely forested. It's a very, very sparsely populated country. But it's all, I mean, I think another like big problem is that it's like many Pacific nations, it's been extremely negatively impacted by a colonial history that probably goes back about 150 years, 200 years maybe, in which time it sort of, I guess, changed hands multiple times. And was a site of various like sort of proxy conflicts in the First and Second World War. So in terms of development and infrastructure, so even just road networks, power supplies, the ability to bring in calibration gases for your instruments, there are lots of challenges facing both, I guess, research and monitoring by local scientists, and also to anybody like us, like international teams who are coming in and trying to establish research projects there. So I think we've been successful in a lot of that. Well, provisionally successful. A lot of that is due to very good relationships with partners in country. So there's a volcanological observatory who are kind of a branch of the government who are tasked with monitoring volcanoes, and we have a good relationship with them now going back a few years. And they then have kind of partnerships with sort of provincial disaster offices. So when we visit a new part of the country, we can kind of make some contacts there, which can be very helpful for getting just support to travel within the country. So getting boat access or trucks or whatever. And then another thing that's really important is making connections with the people who live around the volcano. So a lot of the land is what's called customary land. So it's not owned by the state; it's owned by the people who are indigenous to that area. So another important part of the work is kind of engaging in those kind of interactions and being clear about why you're there, and trying to explain what your research is trying to achieve, and trying to think about how it might, where the possible benefits are for people who are essentially hosting you for a couple of weeks at a time.
So hypothetically, say I'm one of those hosts, what would you tell them when they ask you why you're here, essentially?
So I guess what the angle that we usually take is that there are, I guess, sort of two strands of motivation for the work that we're doing. So one is to understand volcanoes as like a natural phenomenon, and the other is to understand them in terms of their unrest, and try to provide insight into how they work, and whether they are going to erupt similarly to how they have in the past, or whether they're going to erupt soon, or if they're in a state of persistent eruption, like many of these volcanoes are, what the kind of departures from that might look like. And the thing that's very interesting about that latter part is that often the people who are living around these, well, I would, and in fact, no, more than often, I would say consistently, the people we're talking to, so our hosts during this work, have a very good understanding of a large range of the potential hazards from their volcano. They have a lot of understanding of kind of precursory signs that precede eruptions. They have like a pretty rigorous path to escape, like a plan that they can implement to kind of get away. And I think that's really interesting, because that knowledge appears to have got lost centrally. So when you meet people like sort of government officials kind of at a provincial level, they're very much talking to us about, can you provide instrumentation that would monitor this or that volcano? Like, how would we go about setting that up? And like logistically, that's extremely challenging in the middle of like tropical rainforests, say 20 kilometers into the interior of a very like mountainous island, when the island itself is a long way from, the main center of population in the province. But then when you get to that place, the people who live there are then very kind of tuned into the signs of the volcano, and very, I guess, ready to mobilize if things change. So it's an interesting interaction where you're kind of saying, well, we can help you understand the volcano. And they say, well, we actually understand the volcano quite well. So I think it's been very eye-opening that there are different kinds of knowledge about these natural phenomena that we sort of very cliched to say, but I think we feel like we're learning from each other here, and there are different kinds of knowledge that are valuable in both sides of that discussion. But it's very important, I think, to focus on those things and not just talk about sort of kind of arcane research things. Like, you do witness conversations, people who haven't. And I mean, I still catch myself doing this, where you having a conversation with someone and start talking about some specific area of your work. And like, what does that even mean? So it's a good, I think, exercise in trying to like condense down like the sort of key messages of your research. And I think as well, emphasizing that what we're trying to do is not exploitative. And I mean, there's a part of the problems in this part of the world, if I can kind of generalize, is like resource exploitation by like the state or by international companies and things, and this has created a lot of like social tension, sort of episodes of civil unrest, things like this. So it's very important to say, we're not looking for gold, for example. We're not trying to do this for sort of commercial reasons, and I think because people are anxious, having had bad experiences in the past, that people are going to come in, discover something of value, and then kind of exploit it and just disappear, leaving just kind of pollution behind, basically.
In those discussions with local communities, have you learned anything particularly unexpected or interesting about the area that you were visiting? Or
Yeah, I mean, so we were in an island called Bougainville in September of last year.
Is that the island that recently had an independence referendum, I think?
Exactly.
Yeah.
Yes. Yeah. So they had a yeah. Just as an aside, so because this is a quite important context, they had an independence referendum. Politically, it's the island has been part of Papua New Guinea since, I guess, like German occupation, like the mid-19th century, and I guess ethnically and certainly geologically, it's part of the Solomon Islands, or it's more. I mean, part of the Solomon Islands versus part of Papua New Guinea doesn't really mean anything, because these are sort of states that are like the delineations between these like island states is sort of imposed by people not from there, right? So this, I guess, is still coping in many ways with the fallout from this. But one of the sort of more egregious examples is the inclusion of Bougainville in Papua New Guinea. And Bougainville has one of the world's largest porphyry copper deposits. So there was something like 12, 15 years of civil war through the late 80s and 90s between like secessionist fighters in Bougainville and the Papua New Guinea state, that was kind of precipitated by exploitation and pollution, environmental problems around this mine. So this is like a very difficult place to work, particularly when you're kind of initially going in with people from PNG rather than like local people. But anyway, it's amazing. So it's the second time I've been there. It's a really fascinating volcano. The volcano is called Bougainville. And the thing that was really incredible about talking to people about the volcano was they have a number of different ways by which they sort of perceive the volcano is about to erupt. And it was, I found that really remarkable, because it's a volcano that's not monitored at all. Like, so we kind of have satellite observations, but there's not a single instrument on the ground. It's extremely remote. And they were describing to me that, so there are a lot of, like, there's a kind of a big river running down, and a lot of this sort of the headwaters of that come out from underneath the volcano. And they said they observe over a few weeks prior to eruptions, like vegetation drying out and dying back along the banks of the river, because the water temperature is rising, and not to the extent that you would necessarily perceive it, like wading through like what is a big fast flowing river. But apparently that this occurs, and you can observe this phenomenon. And the volcano is kind of, it's essentially like a big pile of overlapping lava flows. It has these sort of multi-month duration effusive eruptions where like just lava kind of pours out of the summit crater, and the whole edifice is just built of these overlapping flows. So it's in a kind of regular state of eruption and quiescence, and alternating back and forth between those. And so they were describing these kind of phenomena that precede the onset of the lava flows. And they talked about kind of hearing, like hearing kind of rock falls increasing on the volcano as I guess it starts to, the upper conduit starts to deform, like as the magma's kind of pushing its way up. But so that was really incredible. And the other thing was that our, so we had a paper a couple of years ago using satellite radar measurements. This was with a colleague at Reading who led the work. And he made these measurements with satellite radar, and sort of built digital elevation models of the volcano over the last sort of, I guess, 10 to 15 years, and then compared those to digital elevation models built from aerial photography over like preceding decades. So we were able to calculate the kind of change in volume of the edifice, and I mean, it's quite crude, but get a sort of mean extrusion rate by which, so the rate at which the volcano was growing. And now the modern edifice of this volcano is about just under 2 kilometers high. And we don't know the shape of the underlying topography very well, so we have a bit of uncertainty. But broadly speaking, we have an estimate of the edifice, and we know the extrusion rate going back a few decades at least. And based on that, the volcano is at most a few centuries old. Like this modern edifice has just grown like a really big rapid pile of lava. And there's interesting things there because it's on the edge of like a sort of big, like a larger volcano with a kind of large sort of summit caldera, and maybe this is a sort of like almost like a parasitic cone that's just grown on the flanks of this other volcano. So we have a kind of vague idea the volcano is very young. Anyway, in the schoolhouse there's a one of the children has done a sketch on the wall of a volcano and has written a story, which is like the origin story of the volcano. And I was asking about this, and they said, yeah, no, that's the story. She just happened to write it down as part of the project. And the story goes that the volcano was, or a volcano was looking for somewhere to live, and he was trying to find a place that was quiet and there were no cockerels, because he was really annoyed by cockerels crowing. So he looked around everywhere and he found this place, and he could hear the wind in the trees, and he could hear the river, and it was all very beautiful. So he started to build himself. He turned himself into a bee, which is a part I couldn't quite get a clear idea of why he had to turn himself into a bee, but he turned himself into a bee, and then he started making like a little pile of earth. And they said, well, this is what bees do. They build nests. Okay. So he was building this nest, and it got bigger and bigger and bigger, and turned into a mound. And people were kind of, and it was basically on this road between the people who live there now and some like a neighboring community, like kind of across the mountains. So people kind of passing along this road kept kicking over the mound and getting really annoyed. This mound was growing and growing and growing, and eventually it grew, and it was a volcano, and it was called Bougainville, and now it's there. And the thing that really struck me about this story, A, it was a cool story, but B, it was the idea that it kind of the volcano's growth cut off this sort of conduit between different communities. And they were talking about, there was a trade route, and we used to be able to, we in this kind of like ancestral sense we would trade nuts with bananas with the people down there, in the way that we would trade with shells for people who come by canoe up to the sea, up the coast. So that was amazing. So the story kind of didn't obviously put an age on the volcano's growth, but it kind of implied this youthfulness, and that it had appeared within the interval of occupation of this part of the island, which was kind of remarkable, and is at least as valid as our kind of slightly arm wavy, lots of caveats, mega uncertainties radar study of the speed of the growth. So yeah, it just really shows that people who live and observe this volcano, that's like a very integral part of their every aspect of their lives. They live on the flanks. They have a huge amount of information for us, and the parts of the expedition where we couldn't fly the drones because it was just pouring with rain, we could sit and have really amazing conversations and get a lot of information out or a lot of new understanding perhaps about the volcano, and it would kind of come in unexpected ways, I think.
I feel that's a beautiful children's book that's just waiting to happen. So it'd be great to ask you how you collect all of these volcanic gases. So I know you just mentioned that you use drones. That sounds quite fun.
Yeah. So
is that driving drones like through gas plumes then, or?
Yeah, that's right. So I've come into this very recently, and I guess the real drivers of this have been a group at the University of Bristol. So a colleague of mine who's now at UCL, called Emma Lou, and a group in Bristol, so a volcanologist called Matt Watson, and two engineers called Tom Richardson and Kieran Wood. I guess that they collectively have been really driving this forward in UK volcanology. So two of the guys, Tom and Kieran, are actually flight engineers. They build drones and understand like flight control, and the kind of remarkable thing about this is, as volcanologists, I'm using drones for quite a long time, but it tends to be, a drone you've bought off the shelf and you fly it over the volcano and you get some kind of cool imagery. Whereas people who are actually experts at building aircraft, and particularly building aircraft that can do like long range autonomous flight, that kind of thing, like the sort of what is kind of unreachable technical capacity for us is their sort of bread and butter. So the drones that they're building are hand launched or take off themselves from the ground next to you, and will go up 2 kilometers altitude and will fly horizontally 10 kilometers altitude. So we can reach the summit of a volcano from a long way away. So in terms of safety, it makes an enormous difference, or just practicality. I mean, there are volcanoes you can't really climb, like Bougainville, It's just under 2 kilometers. It's in the middle of the rainforest, and the edifice itself is just piles of kind of crumbling lava flows, so like loose boulders and things. So the collaboration with the Bristol Flight Lab has been kind of really transformational. So they're building these amazing aircraft, and essentially we put a kind of miniaturized sensor payload inside the fuselage of the aircraft, a little pipe poking out, and have an onboard pump that sucks air, sort of ambient air, through the sensors. So we can take off, and there's a GoPro in the nose of the drone that is kind of relayed back to the pilot. So you can automate the flight, or you can pilot it yourself. And so we can see on the sort of video readout where the plume is, and we can direct Kieran, and he'll fly it back and forward through the plume. And all the time the pump is kind of sucking the volcanic gas into the sensors. And it's fantastic. It's really allowing us to make measurements that are otherwise very, very challenging to do for these kind of steep remote volcanoes.
And does the drones have some kind of GPS tracking signal inside of them? So I imagine you get some lovely maps showing where they were when
exactly.
they get certain readings.
Yeah, exactly. So they have very very accurate, like onboard navigation. So we can measure exactly where the drone was, and in principle you could imagine an aircraft, if it could stay up for a long period of time, you could be mapping out the kind of variable chemistry in different parts of the volcanic plume. Or you could imagine 2 aircraft in parallel, one kind of close to the volcano and one in the downwind plume, and you see how there's a lot of like rapid atmospheric chemistry in volcanic plumes, because lots of different species, lots of different particles, lots of water vapor. So there's lots going on, and a lot of that kind of complexity has only really been modeled in the past. So there might be ways to start making more direct measurements that could really help our understanding of how I guess gas plume chemistry evolves.
I was just going to say, I mean, that sounds amazing. Also in terms of safety, obviously some of these gases aren't going to be too friendly for humans.
That's right.
Collect gases in this way.
So we, I mean, ideally, the volcanic gases you collect would be a temperature of several hundred degrees, because you want that the high temperature is a good sort of first order check as to whether they've interacted with groundwater. So if you're measuring the sort of gas escaping from a vent or a fumarole, and it's only 100 or 200 degrees, chances are it's not purely magmatic gas. It's interacted with groundwater, and the chemistry's been changed in some way, and it's not giving you a sort of it's not giving you the true character of the magmatic volatile content. So it's harder to use for monitoring data. So this actually means, the ideal case would be somewhere like an open vent volcano, somewhere like Stromboli, where you have a magma surface exposed to the air, and you can get right over that and measure the gas as it actually degasses straight off the magma. So the drones may potentially offer us a way to do that. So it'd be very, very dodgy to kind of go and hang out over a crate like an active vent and dangle an instrument in, but you could probably make the case to risk an aircraft to do that. So you're right. It makes a big difference on the safety front. So the conclusion of the Papua New Guinea work at the moment is a kind of an interesting one. So we went into the field to this volcano Bougainville because it's one of the largest sources of sulfur dioxide emissions in the world, and that observation is based on a decade of satellite observations. So if you look at the world's volcanoes over the last decade, Bougainville is like number 3 in terms of sulfur dioxide flux on average. And we were funded to go and make the first measurements of carbon dioxide emissions from this volcano, because there's been lots of work recently understanding volcanic carbon outgassing, and the feeling of a lot of people in our community was, well, we know this is a big sulfur emitter, it's got to be a massive carbon emitter too. So you should go and because generally speaking, most magmas are richer in carbon than sulfur. Anyway, volcanoes do sort of switch on and off, and you can probably see where this is going. But when we were in the field, Bougainville was actually very, very quiet in terms of its activity. So we had good conditions for measurements, but the sulfur dioxide emissions were around an order of magnitude lower than the long-term mean over the last decade. And the way by which we estimate the carbon flux of the volcano is we measure a carbon to sulfur ratio in the plume with our kind of drone instrument payload, and then we multiply that ratio by the sulfur flux we're measuring by remote sensing on the ground. So they're very intimately tied, and I mean, one result might be that we need to do a better job of kind of measuring these more independently. But the result is that the carbon flux of this volcano is very, very low, like much smaller than people had been anticipating. And I think so. The sort of physical reason for this is that when a lot of volcanoes are not in a height and state of activity, especially in the tropics, you do develop a big groundwater sort of hydrothermal system, like a kind of a shallow hydrothermal cap in the volcanic edifice. So it's a pile of like loosely consolidated rock. It rains on it very heavily every afternoon. So it's essentially, in my view, a big sponge. It's full of water, and the gases that are still rising, a lot of them are being dissolved into the water. And they're probably precipitating out as minerals in different cracks and fissures, but they're not really making it to the surface. And as a volcano wakes up from this kind of state, you'd imagine that the hydrothermal system would be boiled off by the heat of the rising magma, and you would start to kind of stream magmatic gases directly through the edifice to the surface again. But this isn't what we have at the moment. So in that sense, the measurements are a little bit disappointing because they're not, we kind of ideally would have been there in a period of very high activity. And it's a tricky place to get to, and there's a long way to go, etc., etc.
So do you predict that it actually would have had higher CO2 emissions than what you found?
Yeah, I think so. I mean, basically, we just measured it, and I mean, if it goes up and down, we measured it in the down period. But I think what this shows that's quite important is that we all know that volcanoes are kind of stochastic, and they switch on and off, and the level of emissions and seismicity and all other kind of manifestations of unrest does go up and down. But as a community, when we're thinking about, I guess, like emissions inventories of volcanism worldwide, we are still quite restricted, especially for carbon dioxide fluxes, which you can't measure by remote sensing from space because you have a big carbon dioxide budget in the background atmosphere. It's really hard to sort of see through that to a volcanic signal. We tend to base our calculations on these short kind of campaign measurements at the great majority of volcanoes. So if you kind of time it wrong and you get there at a very quiet period, and that's just kind of the luck of the draw in a sense, that you're introducing potential biases into this kind of overall picture of volcanic emissions. So I think what we need to do as a community is move away from this kind of, trying to assign a single number like X thousand tons a day of sulfur or carbon to volcanoes, and think in a more kind of dynamic sense and try to capture that variability. That's very hard to do at remote volcanoes because you can't be there all the time measuring them. And this might be, again, to come back to the drones, this might be somewhere where, or like the low cost sensors that the guys in Manchester or another group in Sheffield are trying to build at the moment. This is, these are the kind of motivations we might have for trying to think about how we can actually monitor volcanoes more consistently. Because if we are just going for very short-term campaigns, it's hard to build up a representative picture of what's going on. So I think that's the sort of the consolation result, that it kind of perhaps shows us, or gives us a direction that we need to start moving in terms of how we study volcanoes and their emissions.
Amazing. Well, thank you very much, Brendan. We actually have a final question for you.
Yeah,
so if you could be doing anything else other than looking at volcanic gases, it can be in academia or outside of academia, what would you want to do?
I really like this question, actually. Not necessarily because I have a good answer, but I think it's occasionally fun to put people on the spot and make them reflect on their life choices. I don't know. So we have an allotment. So I like spending time in the allotment, and it's a lot simpler than almost every other part of my life. So yeah, growing vegetables would be kind of class. I guess I don't know. For all that I really like the research I do, I do also like a lot of extracurricular things. Like I like watching football, and I like playing as well when I get the chance. I like baking bread. I like my allotment. So I mean, I think I don't necessarily know what job I would do, but I'm sure I could fill my time.
Obviously, a bread baking, allotment working footballer. That's
Yeah. That's a
Well,
classic role.
Yeah, I mean, I think there's scope to develop it. I don't know how many footballers have allotments.
Exactly.
I think more probably could and should.
Yeah.
Because you can't train all the time. You get exhausted. So
Yeah. Are you able to get out to your allotment much at the moment in the current situation? Or?
yeah, well, it's not too far. I mean, I should. Yeah, I don't know I did it. So actually, I was encouraged the day after the lockdown was announced. Michael Gove was questioned about this and did admit under questioning that going to your allotment did count as legitimate daily exercise.
Yeah, I guess if you can walk there, it's probably fine.
Yeah. So it's okay. It's close enough that we can get there, and but it's sort of at this point in the year, it's early enough that we're growing a lot of things from seed at home. So it's going to be, I guess, in a month's time when we really want to get up there and plant things out. So yeah, watch this space, I guess. I hope so.
Fantastic.
I mean,
we'll have to start Marrow Watch or something.
Well, thank you very much, Brendan.
All right, no, pleasure. Thanks all of you for the invitation. I really enjoyed it.
Yeah, it was really nice to talk to you. Yes, so if you'd like more Earth and planetary science content, we have got lots of links in the thumbnail here for our Twitter, Facebook, and our blog. And thank you very much, everyone, for listening. Thanks again to Brendan, and see you next week.
See you later.
Bye.
Bye.